Okay, so let's go ahead and get started here. This is the third, and depending on how you want to think about things, either the last or second to last lecture that I'm going to give specifically about proving that things are NP hard. So if you recall, at least morally, what it means for a problem to be NP hard is that attempting to prove that there's no polynomial time algorithm to solve the problem. More formally, what we are trying to show is that if there were a polynomial time algorithm to solve this particular problem, then for any problem whose answer we can verify in polynomial time, given an explicit proof of correctness as part of the solution, we could solve from scratch in polynomial time. This is the so-called P versus NP problem. And the way that one proves that a problem is NP hard is by taking a known NP hard problem and reducing it to the problem that you're interested in. So at a fundamental level, this is a proof by contradiction. So I will assume, for example, for the sake of argument, that there is a polynomial time algorithm to finish an arbitrary level of Super Mario Brothers. And I will use this supposed polynomial time algorithm to solve some problem that I've already thought about being NP hard in polynomial time. In this case, 3-sat. So the way that the typical reduction argument works is I start with an arbitrary instance of the known NP hard problem. For 3-sat, this means I start with a Boolean formula in a particular special form, namely it's an AND of a bunch of clauses where each clause is an OR of a bunch of exactly 3 literals, where each literal is either a variable or its negation. And given this arbitrary 3CNF Boolean formula, I construct out of it a level for Super Mario Brothers. And then I prove that it is impossible, that Mario can win the level, reaching the flag, if and only if the formula that I started with was satisfiable. And like there was an assignment to the variables that made the entire expression evaluate to true. So it's important to keep in mind the direction in which the reduction argument goes. You're given an arbitrary 3CNF formula, and you want to transform it into a special level of Super Mario Brothers, which you then pass to this fictional algorithm, and not you start with an arbitrary level of Super Mario Brothers and play it. Right? The goal is not actually to play Super Mario Brothers. The goal is to prove that it's hard to play Super Mario Brothers. Right? So you don't actually attempt to play the levels, and in particular the levels that actually come with Super Mario Brothers can be solved in constant time because they fit in a little Nintendo cartridge that has 8 kilobytes of memory or something. What you actually want, start with an arbitrary Boolean formula, which may be terabytes in length, and construct from it a sort of generalized Super Mario level, which may be light years on a side, and then you want to be able to play. You want to assume that you can play this in time only polynomial in the size of the level, and thereby derive a polynomial time algorithm for 3-sat. So this particular reduction comes from a paper that came up on the archive 4 years ago by two of these people are co-authors of mine, Greg and Eric, and Alan Guo was, I believe, a student of Eric's at MIT, and Giovanni Viglietta is a researcher in Italy. And so they wrote this paper showing that lots and lots and lots of classic Nintendo games are hard. And the way they did this was by coming up with a kind of meta-reduction. They said, let's not try to reduce 3-sat straight to Super Mario, straight to Legend of Zelda, straight to Donkey Kong Country 3, because that's going to make the paper too long. What we're going to do is then we're going to say all of these reductions have the same special structure. I'm going to imagine first this sort of abstract game where I have a player that has to start over here in the start part. I'm going to go into something that resembles a variable gadget, and with the semantics here is when the player goes into the variable room, they must either exit through the edge labeled with the variable, or they must exit through the edge labeled with its negation. This chooses a value for that variable. And then they must go up to the next variable gadget. They're not allowed to go down. Right? So these little circles, you can go in from the top and out to the top. You can't go in from the top and out to the bottom, or else things won't work. And so I go into the next variable, either from one side or the other, and then I decide what the value for y is, and then I go up to this variable and I decide what the value of z is. And then once I've done choosing the value for z, I then start the checking phase to verify that the values that I've chosen for these variables satisfy the Boolean formula that I was given as the input to create this level. And so I have another gadget for every clause. And the idea is that somehow what I've done when I've visited these nodes from the variable gadgets is I've unlocked a door. So when I choose x to be true, I unlock a door here. And then later, when I want to check whether a clause is satisfied, I say, well, maybe x is true. In which case, I can go up through the open door and then back down into the next clause. Okay. So this is the way the check part of the algorithm, the level works. I go into a clause, and through one of these three literals, I need to be able to go up through an open door and back down. And then I go to the next clause, I go up through an open door, back down. And the next clause, up through an open door, back down. Next up, through an open door, down, and then to the finish, where, thank you, Mario, but the princess is in another castle. Okay. And so in actually making this, so the semantics encode a kind of procedure for verifying that a 3-sat formula is satisfiable. First, I set the variables. Then I check for each clause whether that clause is satisfied by the variable assignment I've chosen. But this is an actual geometric picture here. So if I actually want to turn this into something about Super Mario, there are a few details that I have to fill in. Namely, what goes on inside the start gadget? What goes on inside this variable gadget that forces you to make a left or right choice? What goes on inside this lock that forces you to, allows you first to unlock things, and then later when you come up from a clause, only survive if something is unlocked? What goes on inside these clause gadgets? How do you win? And then somewhat more subtly, how do you make these wires cross? Right? So you can imagine each of these wires, these are hallways that the character walks through, but Super Mario lives in flatland. So if two hallways cross, and I don't enforce something here, then maybe Mario can do something really weird, like I'll go, like this, and just sort of bypass all the interesting stuff to go straight to the finish. I have to somehow design my gadgets so that Mario cannot follow a path through the level that doesn't correspond to some semantics about the original formula. So without going into an incredible amount of detail here, the way that Greg and Eric and company did this, the start gadget is Super Mario jumps up and gets a mushroom, and then he gets to be tall, and then he goes through a gadget that you can only get through if you're tall. So Big Mario can jump higher. The finish gadget in particular is tall Mario breaks this brick and jumps out and jumps on the flag. If Mario was little when he gets to that point, sorry, you don't get to finish the level. The variable gadget looks like this. I come in from the top, either from the left or the right. This is way too high for Mario to jump, so Mario goes down, and then he has a choice to either fall down on the left or fall down on the right. Notice that Mario cannot go backwards through this gadget. It's a one-way choice. This is the claws gadget. So the bottom of the claws gadget, these are connected to ultimately connected to the literals, and these are the locks that I was talking about. So say this is a clause corresponding, this gadget corresponds to the clause A or B or C bar. Right? So actually write that in, A, B, C bar. So as Mario goes through the level, he decides, I'm going to set B to be true. So in the variable gadget corresponding to B, he goes down, he walks through the level into the claws gadget, and he comes up from below as Big Mario, and he hits this mystery block, which contains a star. If you played Mario, you know that the block stays there. So he can't actually go into the claws gadget. He has no choice but to sort of backtrack out to the next variable gadget or to begin the checking phase. But later, when Mario is checking all the clauses in the checking phase, Mario comes in from the left. He's big enough that he can jump over and grab the star if it's there. And if you grab the star, you're fireproof. And so you can run through the fire. But if there's no star waiting, you're dead. Okay, so the only way to get through this clause gadget when you're in the checking phase is to have already in the past come up from a variable gadget and knocked on this thing to create a star. Okay, so in other words, you can only get through the clause gadget if you've decided to set a literal to be true, but you can only set either a variable to be true or its negation to be true because you have this binary choice in the variable gadgets. And then the most subtle one is how do you set up a way for various tunnels that Mario goes through to cross. And so we have a crossover gadget. So in this case, Mario can come in from down here, fall down, hop up, break through, and leave that way as Big Mario. Or Mario comes in over here, turns into Little Mario because that, I believe the technical name here is Koopa Troopa. Turns him into Little Mario, but then he can jump up here and crawl under this little gate. Big Mario needs to be able to go up. Sorry, not. So Little Mario does this. There's a mushroom under here. Little Mario comes and turns back into Big Mario and goes up. Big Mario would go la 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 through the brick wall, and up. Now, there's an additional subtlety in the proof that, Big Mario can't go either to the left or to the right because Big Mario can't get under these gates. The only choice is to leave going up. Also, you notice you can't go from the top and go down. If you're coming in as Big Mario from the upper right, you can't actually get through that brick. So there are only two ways to get through this gadget. And moreover, once you've gone through the gadget once, you can still go through the gadget the other way, no matter which order you do it. But you can't go through the gadget horizontally more than once. So putting all these pieces together, they proved it is NP hard to decide, given an arbitrary level of Super Mario Brothers, if you can finish the level. So in some intrinsic way, playing Super Mario requires you to consider an exponential number of possible paths through the level. And as far as we know, the only way to figure out whether a given level of Super Mario is finishable is to try all possible paths and for almost all of them decide, okay, I'm going to die, I'll just sit here and run out of time. Okay, start over. Let's try going left this time instead of right. At the first gate, is that you can only do this in exponential time. Okay. So there are a surprising number of technical details in getting this proof exactly right, mostly involving making sure that Mario can't diverge from the script that is written in the sense of, I want to set the variables and then I want to check the clauses. No left turns into a right turn only kind of thing. And that actually takes quite a bit of effort to get it right. Yes?
I'm a little bit fuzzy on the details of when this requirement is enforced by the game, but isn't there something about how you can't walk past the left end of the screen?
So one of the things about proving these general results about generalizations of the game is the actual game, you can only scroll horizontally, and you, up to some constant buffer size, can only move to the right. Now, this particular reduction that I showed you violates both of those constraints. You need to be able to move up and down, and you need to be able to move arbitrarily to the left. So it's kind of, you have to decide what generalization of Super Mario Brothers you're actually going to
So the
study.
generalization came with the data of how big that buffer is, then you could just make it longer.
Right. So there's a follow-up paper which is going to be published soon, which allows you to do things like, apparently there are some really non-obvious glitches inside Super Mario that if you're Little Mario, you can actually break through brick walls if you time your jumps exactly right. So when you hit the brick above you, it sort of goes up a little bit. And while it's up, that's actually an open gate that you can walk through. So they say, okay, look, we're going to allow all the glitches that we know about, and we're going to only allow a certain vertical size. I think they still need to let him move to the left. So you get a stronger result. Yeah, so you have to be careful about exactly how you define the problem. Yeah?
What is the biggest computation meaning if you get stuck inside the reduction? Like if you kill the...
That means, well, okay, so let's be careful about what we're actually proving here. It is possible, I shouldn't say I can, to win this level if and only if the input formula is satisfiable. So there are two things that I need to do to actually win the level. The first thing I have to do is choose a satisfying assignment for the formula. And the second thing I have to do is I have to follow the script that allows me to finish the level when I have a satisfying assignment. So if I get stuck, it could be because Well, I just followed one of the many ways to lose the level. And it doesn't tell me anything about whether the level is winnable. Or it could be that there's no way to win the level. And sort of the important philosophical point is there's really no way to tell which that is. Did I not find a solution because there is no solution, or did I not find a solution because I just haven't tried the right combination of possibilities? Okay? So, again, to prove some problem X is NP hard. Step 1, I'm going to choose a known NP hard problem, which I'll call Y. And at the moment, the choices we have are circuit satisfiability, formula satisfiability, 3 satisfiability, maximum independent set, maximum clique, minimum vertex cover, 3 color, and Super Mario Brothers. Okay? So I choose a problem out of this collection that hopefully in some way resembles the problem that I'm trying to prove is hard, or it's 3-sat. It's always, when all else fails, it's one of these two. And it's never Super Mario Brothers. And then step 2 is reduce y to x in polynomial time. And what this means is that I want to design an algorithm for y using as a black box this fictional algorithm for x. This involves doing something to the input, and occasionally it involves doing something to the output. But this thing in the middle is, you should just imagine that this is an imaginary algorithm that somehow solves arbitrary instances of whatever problem x is in polynomial time. Right? Okay. So imagine that there is a special magic algorithm that automatically plays Super Mario. Then I'm going to use that Super Mario-matic algorithm to solve 3-sat by designing first an input transformation that says, given an arbitrary 3CNF formula, I'm going to transform it into a level from Mario. Then my magic black box decides whether it's possible to win that level from Mario. And if it is, my output transformation in this case is just return that bit. So if the black box for Super Mario says, yes, you can win this level, then I'll output, yes, this formula is satisfiable. And if this black box says, no, you can't win this level, Mario, then I will output, no, that formula you gave me is not satisfiable. And then the last thing to do is, of course, to prove it works, which typically involves 2 steps. Prove that if the formula is satisfiable, then Mario can win, and then prove if Mario can win, then the formula is satisfiable. It's very important to remember that on the one hand, the reduction is only going in one direction. I take an arbitrary formula and I turn it into a level of Super Mario. I don't consider what happens to arbitrary Super Mario levels. It doesn't matter. But when I'm doing the proof has to go both ways. given an arbitrary formula, that formula is satisfiable, then the resulting Super Mario level is winnable. Given an arbitrary Boolean formula, if that formula is not satisfiable, then there is no way to win the resulting Super Mario level. Okay. One of the mistakes that is very easy to make is to come up with a reduction for which only half of the proof works. Okay. And what makes doing this NP hardness stuff actually difficult is remembering that not only do you have to take a good instance of y and transform it into a good instance of x, but given an arbitrary instance of y, if it turns into a good instance of x, it had better be a good instance of y. Right? There's no way to get false positives. There's no way to get false negatives. Right? So what I want to do, next is I want to walk through in slightly more detail 2 more NP hardness reductions, one serious and one somewhat frivolous. And after I go through the one that's a bit more serious, there's another question that needs to be asked is, this list up here after point 1 is going to get very long. How do you decide what problem to reduce from? And there's no algorithm for choosing this problem. There's some intuition, there's some rules of thumb that I can suggest. If all else fails, it's probably 3 sat. So the problem that I want to think about next is the Hamiltonian cycle problem. And in particular, I'm going to look at the directed version of the Hamiltonian cycle problem. So this is a problem where the input is a graph, and there's a choice of whether the graph should be directed or undirected. This might end up being a problem on homework 10. You can reduce from one to the other, and so you just need to pick one and prove that's hard. And then there's a relatively simpler transformation to turn it into the other one. And so I'm going to start with the directed version. The input is a directed graph, which I'll call G. The output is a cycle that visits each vertex. This is a cycle in G. It visits every vertex in G exactly once. Okay, so this is a Hamiltonian cycle in this graph. Okay, so if I'm given all of the edges in this graph as my input, then the answer to this question is, well, again, there's a subtlety that it turns out not to matter. I can either say, yes, there is a Hamiltonian cycle, and that's enough, or I could require that you actually compute the Hamiltonian cycle and output. So for the yes-no version, which is the one that I'm going to be thinking about, the answer for this particular graph is yes. Here is the Hamiltonian cycle. Okay. Another way to think about how a Hamiltonian cycle, what it is, you want to choose a permutation of the vertices, so that in the permutation, adjacent pairs of vertices are connected by edges. Of course, I left one rather important point out, which is I said the graph was directed, so I really do mean something like this. And maybe there's an edges going back like that. Okay?
Forgot the one on top.
Thank you. Okay? So I'm given this complicated collection of red and black things. I want to return yes because this black cycle is inside the graph. Okay, so in the notes, there are actually two proofs. There's a proof using the minimum vertex cover problem, and there's the proof I'm going to show you now. The proof from vertex, the reduction from vertex cover, is actually the one that Karp described in his 1972 paper that listed the first 23 NP hard problems, which won him the Turing Award. But I think the proof I'm going to show you, which is a little bit more recent, is simpler. Okay. So I need to choose a problem from this list. I already told you, you can do this from minimum vertex cover, and these three problems are really all the same, so you could have done it from any one of these. It's a problem about graphs, so maybe it makes sense that I'd want to start with this. Three color doesn't really make sense because there's no threes in the problem. I'm not choosing threes of anything. I'm not assigning values to the vertices. I'm trying to impose an order on the vertices. So nothing seems to be good, so I'm going to punt and use 3-sat. Okay. So I'm going to prove this is NP hard. By a reduction from 3-sat. Okay? So again, when I say a reduction from 3-sat, that means given an arbitrary formula, I need to transform it into a graph that has a Hamiltonian cycle if and only if that original formula was satisfiable. And just like when we did vertex cover or independent set, just like when we did 3-color, just like when we did Super Mario, there are going to be pieces of this output graph that try to enforce some semantics about the formula that we're starting with. Okay, so I'm given an arbitrary 3CNF formula phi. I need to produce a graph G. Okay, so the first thing I'm going to do is I'm going to have a gadget, a subgraph that corresponds to each of the variables. And I want to create this in a way that somehow enforces a binary choice on this variable. Okay. So variable gadgets. Okay, so for each variable x, I'm going to transform it into a chain of vertices which are connected in what looks like a doubly linked list. Okay? There'll be one of these for each variable. For now, let me not explain what the length of this list is. That'll come up in a minute. Obviously, if you wanted to, you could make this arbitrarily long. The idea now is that if I imagine, the endpoints of this doubly linked list are going to be connected to the rest of the graph somehow. If a Hamiltonian cycle lives in the graph G, it has to pass through each of these vertices exactly once. And because every one of these nodes has only in degree 2 and out degree 2, and they're connected in sequence, there are only two ways to traverse this list. start at the left end and go all the way to the right, or start at the right end and go all the way to the left. And these are going to correspond to setting the variable x to true or false, intuitively. Okay? The intuition is, if I want to set the variable to true, I want to try to get my Hamiltonian cycle to start on the left and move to the right. If I want to set my variable to be false, I should try to start on the right and move all the way to the left. There's no way that I can stop in the middle and back up, because that would require me to visit a vertex more than once. Okay. Now, the various vertex gadgets, which I'm just going to draw as these sort of bars for now. What I'm going to do is I'm going to arrange something where I need to make an independent decision for every variable. So I'm going to start with, the vertex gadget for variable A, and I'm going to connect both ends of A to the variable gadget for B by directed edges. And then I'm going to connect both ends of the variable gadget for B to the variable gadget for C and D, and so on. And eventually I get to Z, and then I connect back up to A. Now again, I have to think about the false starts a little bit. This is going to be connected like that, and then this is going to have edges coming down from above, from the previous variable gadget. I need some way of enforcing the fact that you have to go through these gadgets, whatever they actually are. And the idea is, if I come into this vertex on the right end of A, and I decide not to go through the gadget, I just go down to one of the endpoints of B, then I haven't visited this neighbor of the right endpoint of A. But then if the Hamiltonian cycle later has to visit this node, it has nowhere to go. Right? So if I follow an illegal path like this, then later I guess I have to come into this vertex near the right end from the left, but then I get stuck. There's no way for me to go without revisiting a vertex that I already visited before. So with the graph set up as it stands, the only choices I have are, if I want a Hamiltonian cycle, is I'm going to start at somewhere in one end of vertex A, at the left end if I want A to be true, and at the right end if I want A to be false. I traverse all the way to the end of the gadget for A, and then I have a choice of which end to visit next for B, and then but whatever choice I make, I have to traverse the entire gadget for B, then the entire gadget for C, then the entire gadget for D, and then I can close the loop. And so this particular setting of the gadgets corresponds to the variable assignment: A is true, B is true, C is false, D is true. Every Hamiltonian cycle in the graph on the left corresponds to one of the 16 possible choices for the variables A, B, C, and D. Okay. So far, I've produced a graph that always has a Hamiltonian cycle. In fact, it always has, for a starting formula with n variables, it always has 2 to the n Hamiltonian cycles. So it seems the answer is always yes. I've forgotten something. Yeah.
What's the significance of the length of the chain?
I haven't gotten there yet. For now, make it as long as you like. I think it needs to be at least 3 vertices long for the proof to work. But just think of it as an arbitrarily long chain for now. Yeah.
You might not have the empty formula.
I might not have the empty formula. I've set up gadgets for the variables, but there's a piece of the input that I haven't used. namely the formula. In particular, I need a gadget for each clause. Okay? So there's what the clause gadgets look like. Let me just zoom over here on the left to show you the example. So again, here I've chosen a particular Boolean formula. This is in fact the same Boolean formula that I used to describe the reduction for 3-color. Okay? So I have a clause, A or B or C. So for this clause, I'm going to add a single vertex. It's floating. You really want to imagine these red vertices are floating off the screen. You've got this grid laid down for the variable gadgets. And now I'm going to add a bridge, which has a nice little peak here, which consists of, it lines up with between the first 2 columns of vertices for the first clause, between the 3rd and 4th vertex for the second clause, between the 5th and 6th vertex for the 3rd clause, and so on. So the answer to your question is, what is the length of these chains? It's twice the number of clauses. Okay. Now, the way the clause gadget is designed is that because I have a true literal at the beginning of the clause, I'm going to direct an edge from the variable gadget for that literal, but I'm going to do it from the vertex on the left to the clause vertex to the vertex on the right. And so now if you want to imagine that big Hamiltonian circuit thing as a Super Mario level, Mario needs to traverse through the graph, visiting every vertex. When Mario reaches that vertex over there on the left for A, he can hop down, grab the coin at this clause vertex, and then climb back up. And so intuitively, he can only do that if he's already decided that A is true. So he's starting on the left, and he's moving to the right. So just for a brief moment, he diverges from the canonical Hamiltonian cycle for a particular variable assignment. And he says, oh, I can hop down and grab that coin and then hop back up. Again, B, because B is a true literal, I'm going to come from the left to the right. Because C is a true literal, I'm going to go from the left to the right. Then to the next clause, I have here a negated literal, C bar. Then for that negated literal, come on, you can do it. Oh, come on. Thank you. That negated literal, I'm going to go connect these 2 vertices in the variable gadget for C in the column that corresponds to this clause, but I'm going to go from the right vertex to the clause vertex to the left. And so if Mario's decided, after he's finished with the gadgets for B, hey, I want to set C to be false. So Mario's going to come over here and walk through the variable gadget for C and say, oh, I can hop up, grab this coin, and hop back down. Okay. And I do the same thing for every one of the clauses. I establish a new vertex that corresponds to each clause. Each of these new vertices has 3 incoming edges and 3 outgoing edges, which connect in pairs to the corresponding variable gadgets, but oriented from left to right if the literal is positive, and oriented from right to left if the literal is negative. And so this particular Boolean formula happens to be satisfiable. I can set B to be true. I can set A to be true, B to be true, C to be false, and D to be true. And the way that I describe my Hamiltonian cycle is, given if the formula is satisfiable, I can pick out one true literal in each clause. And in this case, I chose a different satisfying assignment than when I was talking about 3 coloring. So in the first clause, I choose the literal B, in the second C bar, in the third D, and the fourth A. Then, because A is true, I'm going to start at the left end of A and traverse, but whenever I reach the variables that correspond to a clause that A is the chosen literal to satisfy it, I'm going to hop down, grab that token, and hop back up. Then I decided B was true. The first clause is satisfied by B, so the first clause gadget, I hop down, grab the coin, hop back up, then zoom to the end. C is false, so that satisfies the second clause. And D is true, that satisfies the third clause. In this particular case, I chose an example because it made the picture look good, that each of the variables has one literal that satisfies exactly one of the clauses. In general, that's not going to be true. But for every clause, I need to identify one true literal that's going to correspond to the one detour I take to reach that corresponding clause vertex. And so if I walk through this argument carefully, what it implies is if the original formula is satisfiable, then there is a Hamiltonian cycle in this graph that I've constructed. Am I done? I have to prove the other way. I need to prove an if and only if statement, and I've only proved one of the ifs. Okay? I need to go the other direction that says if there is a Hamiltonian cycle in this graph, it means that the formula is satisfiable. And I started working towards the proof of this when I said things like, any Hamiltonian cycle that goes through a vertex gadget must go all the way through, otherwise there's going to be some unvisited vertex in the middle, or some vertex I've visited twice. So what I need to do to finish the proof is to argue that this is the only kind of Hamiltonian cycle in the graph. The only way I can get a Hamiltonian cycle is if it has exactly this structure that I've just built from a satisfying assignment. And so, among other things, I need to show that when I put this graph together, it's not possible for me to, say, enter a clause gadget from variable A and then leave that same clause gadget into variable B. Okay. Which, why can't I have something that looks like this, for example, as part of my Hamiltonian cycle? Anyone want to take a stab at that argument? Why is this particular path through the graph not part of any Hamiltonian cycle?
You won't be able to reach the vertex on the right.
Right, so among other things, this vertex I'll never be able to reach. Or if I do reach it, rather, where do I go next? Right? Well, maybe this is a little easier to see if I think about something in the middle, but there's a few more cases to think about on the end. Say I came from above. One possibility is I'll have to leave to below, but now let me think about this vertex. Right, so this vertex is actually okay, the one on the right side of B. But the one that's sort of next in line in A, from where I escaped the A gadget, I started on the right side of A and it started moving to the left, and then I left the A gadget and never came back. That next vertex in the A gadget, it has incoming vertices, it has incoming edges like this. And those are the only incoming edges. So I couldn't have come from the right because I've already decided what to do from the vertex on the right. So this edge isn't really there. So I must have come in from the left. But now I have to figure out, where to go next. And as you might guess, this is starting to get a little thorny, right? That because, oh, well, I can go down. Sorry. So from here, well, clearly I have to go down because that's the only place I can go. But if you follow this logic long enough, eventually you realize you will in fact get stuck. There's just you're going to get stuck if you try to do that. You're going to go down here, and then where do you go? And then, oh wait, you've gone to some other gadget the wrong way. So this, if I go to the left, then I have to think about this gadget. If you chase the logic far enough, and I think doing this formally actually involves doing some sort of induction argument. What you end up proving is that every Hamiltonian cycle in G corresponds to a satisfying assignment for the original formula theory. This is the hard part. All right. Because there are lots of false starts that I could make. I have to show that none of them actually work out.
If we actually wanted to compute the satisfying assignment, do the cycles have to be of a nice enough form that do that?
The cycles have to be of this precise form, which means the assignment is, do I traverse an edge in the A gadget from left to right or from right to left? That tells you whether A is true or false. Yeah?
This one you prove by if A then B, and then if B then A is since it's correct. I think you also mentioned that if A then B, if not A then not B, that also.
Right, so if not A, then not B is logically equivalent to if B, then A. So you can prove either the implication or it's contrapositive. It doesn't matter. Right, so one way that I could try to argue this is if the formula is not satisfiable, then there is not a satisfying assignment. The only problem with trying to argue that way is that there isn't an easy way to argue about a formula not being satisfiable. That's, in fact, this is this asymmetry between yeses and nos in the definition of NP. It's very easy to talk about, oh, if a formula is satisfied, if it is satisfiable, then here is a satisfying assignment. Boom. This is a proof that it's satisfiable. And I carry that proof forward into a proof that the graph is Hamiltonian. But if there's not a satisfying assignment, I don't have a thing, right? So it's better to say, if the graph is Hamiltonian, boom, here's my Hamiltonian cycle, and now I can extract from that a satisfying assignment. Yeah?
So how do you know when you've exhausted all the cases?
By being extremely thorough. Like literally to say, here are my cases, 1, 2, 3, 4. And before you read the rest of the proof, say, are there any other cases? And then if you're satisfied that this really is an exhaustive list, then case 1, proof. Is that really a proof in case 1? And maybe this involves case 1, A, B, C, D. Right? This is part of the reason why, like in the induction problem on midterm 1, explicit case analysis, it really is much easier to verify that a proof is correct. And therefore, it's much easier to produce a non-trivial proof. If you write it in a form, these are the cases, and then for each one, what to do. So you only have to look at the left inch of the page to see that you've actually done an exhaustive analysis. Okay. So let's go back to here, and add Hamiltonian cycle to the list. Now, there are a bunch of variants on Hamiltonian cycle. For example, I reduced to the directed version of Hamiltonian cycle, where I'm given a directed graph. The undirected version is also NP Hard, where I want to find a Hamiltonian cycle in an undirected graph. Another version of this is Hamiltonian path. I don't want a cycle, I want a path. Even if you nail down the endpoints of the path, let's say I want a path from here to there that touches every vertex. Another immediate variant of this is find the longest cycle in the graph that visits each vertex at most once. Equivalently, or symmetrically, find the shortest closed walk in the graph that visits each vertex at least once. Substitute closed for open, now you're looking for longest path or shortest covering walk. And then you could put weights on the edges and ask for the Hamiltonian cycle of minimum total length, where you add, instead of just counting the edges as being, 1, 1, 1, 1, and then all Hamiltonian cycles would have length equal to the number of vertices. Now I put a value on the edges, and this problem has a name. You know it. This is the traveling salesman problem. Right? So the traveling salesman problem is hard even if every weight is 1. Because then you're just asking, is there a Hamiltonian cycle? Okay. And again, there's the traveling salesman cycle problem and the traveling salesman path problem, and it could be directed, it could be undirected. These are all NP hard. Okay. There are a few other canonical problems, which I'm not going to show you the reductions for, although you can find them in the notes. The one that I haven't talked about and won't, that is really perhaps one of the ones that's the most important to think about, is what's called the partition problem. So the input to the partition problem is a set of integers which are all positive. And the question is it possible to take this set of integers and split it into 2 subsets? Every number in the original set appears in one of these 2, such that the sum of the elements on the left subset is equal to the sum of the elements in the right subset. Okay. So each of us has a certain amount of money in our wallets. Is it possible to have some subset of the people stand on that side of the room, and the rest, everybody else, stand on the other side of the room, so that the total amount of money over there is equal to the total amount of money over there? That's NP hard. The last one, can't spell, called 3 partition, is not partitioned into 3 sets. That would be too easy. But rather, partition into sets of size 3. So, is it possible to say, you 3 people go over there, you 3 people go over there, you 3 people go over here, you 3 people go over there, you 3 people go over there, and every one of these teams of 3 has exactly the same amount of money. Okay, so you're given a bag of 3n integers. You want to split it into n sets of 3 integers each, so that all the sums are identical. Okay. So partition and 3 partition have several variants and extensions. You may have heard of something called subset sum. I have a bag of integers. Can I split off a subset that has whose sum is a particular value? This is a slight generalization of partition. It's still NP hard. Then, if you attach weights to the integers instead of just the values, and I want to choose a subset where I have a constraint on the weight and I want to maximize the value. This is called the knapsack problem. Again, it eventually boils down to partition. There's a bunch of things involving bin packing and scheduling that boil down to partition or three partition. Given these various choices of all these problems, when you're facing a brand new problem and you want to figure out, I want to prove this is NP hard, how do I choose the problem that I start with? I'm in a final exam, I've got 30 minutes, I'm not going to want to waste my time going down blind alleys. What is a good strategy for choosing the problem to reduce from? Okay, so maybe pairwise isn't the right choice. Let's say binary. So binary choices. I mean, I'm given a set of things, and I want to split them into two subsets, or I want to color some of them white and some of them black, or some of them are going to vote for Bernie and some of them are going to vote for Hillary, or some of them are going to move to Iceland and some of them are going to move to Australia, subject to some constraints, right? The canonical version of this is some version of satisfiability, where the binary choices correspond to the truth values for the variables. So if I'm trying to show something about, some people are going to move to Iceland and some are going to move to Australia, I need to set up some sort of correspondence where each person corresponds to one of the variables in my input formula, and the person is allowed to move to Iceland if that variable is true, and they're allowed to move to Australia if the variable is false. And somehow the constraints have to be satisfied in a way that corresponds to the satisfiability of this formula. The other possibility is partition. So I want to move, half the people in this room are going to move to Iceland, and half the people in this room are going to move to Australia, and I want the total height of everyone who moves to Australia to be equal to the total height of everyone who moves to Iceland. This is the partition problem. So the choice between SAT and partition depends on really whether you have logical constraints or if you have numerical constraints. Another possibility is you have, choices from a small set. Everybody here has to decide whether they'd rather watch a football game, a basketball game, a baseball game, or a badminton game. Subject to some constraints about people knowing each other, doing different things. This is graph coloring, right? And the choice of the set that I assign the person to somehow corresponds to the color that I assign to a node in the graph. If I'm trying to choose an ordering, or I'm trying to choose a permutation, so if I saw Jacobi's problem for the first time, given an n by n array of numbers, how do you permute the rows of the matrix so that the sum of the elements along the diagonal is as large as possible? If I were to set out to prove that this is NP hard, first I'd fail because it isn't. But if I were to say the most likely thing, it would be Hamiltonian cycle or Hamiltonian path, because that's a question about ordering. There are other versions of this, like how do you permute the rows and columns so that some more complicated version is as large as possible, which are NP hard. If I want to find a small subset that is as small as possible but satisfies some condition, this is probably going to reduce from vertex cover. If I want to find a large subset satisfying some condition, this is probably going to reduce from max independent set or maximum clique. If I want to choose, partition into lots of different subsets, probably this is where I would want to use 3 partition, because again, 3 partition means partition into sets of size 3, not partition into 3 sets. And then finally, if there's a 3 in it, 3 sat or 3 color or 3 partition. Interestingly, 2 sat, 2 color, and 2 partition are all solvable in polynomial time. And I have no idea, probably 3 sat. Okay. Okay. So, rule of thumb for how to actually choose the problem. This doesn't always work. Of course, in principle, it always works, because all of these problems have reductions to each other. Because by the Cook-Levin theorem, every one of these problems can be reduced to circuit satisfiability. And circuit satisfiability can be reduced to 3 sat, and 3 sat can be reduced to 3 color, and 3 color can be reduced to, whatever problem you're interested in. But the question is, in terms of getting a short proof that's relatively direct, this rule of thumb is not always going to give you the right answer, which is why often people just find 3 sat. Sometimes circuit sat. Okay.
The homework exam question
Yeah.
well, it's useful.
Yeah. No, I mean, and I don't just mean homework or exam questions. I mean, on the occasions when I've had to prove things NP hard in my own research, this is the pattern that I start with, and most of the time it works. All right. So the last thing that I want to describe, and again, just given the time, I'm not going to be able to go into much in the way of details. Is another frivolous version of frivolous problem. This is about a game, which in the U.S. There's a version of this game called Checkers, which is played on an 8x8 grid with red and black squares and red and black pieces. And the basic idea of the game is originally the pieces are lined up along the edge of the board. In a single move, you can either move a piece diagonally 1 step, or you can jump over something, or if you've been to the end of the board, you're a king and you can move backwards and you can jump and you can capture backwards. But this is not the most popular version of this game, although that it's fairly popular in what English-speaking people think of as the world: the US, Canada, the UK, Australia, basically people who speak English. The more popular version of this game, international drafts, is played on a 10x10 board, and most of the rules are the same. But there are a few very important key differences. The first key difference between international drafts and standard checkers is the so-called flying king rule. Okay, so in standard checkers, I'm allowed to capture a piece by moving over diagonally 1 step, and then this piece goes away. If this piece is a king, I can also do that backwards. But the interesting thing is, in the international version of the game, I'm allowed to jump along take long diagonal steps. So as long as the piece that I want to capture is along the same diagonal, I can jump over it. In fact, I can jump any distance I want over it as long as I stay on the same diagonal. And then that piece is dead. And at the end of the turn, it will be removed from the board. Okay? So this is a really significant change in the game because normal American checkers, you're hopping locally. International drafts, you're allowed to make global jumps. So I can jump this king over this piece to land here, and then over this piece to land here, and so on in this little spirally pattern in one move. Okay? That's the first difference. The second difference is that you must capture the maximum number of pieces. So in the official rules of checkers as it's played in the US, if you are able to capture one of your opponent's pieces, you must capture one of your opponent's pieces. If after capturing that piece, you can capture another one of your opponent's pieces, you must capture another one of your opponent's pieces. But locally, you're allowed to make whatever choices you want. If there is a way to capture, you can take any capture you want. After that, if there's another choice, you can take any choice you want. In international drafts, you must think globally. It is against the rules to capture 5 pieces if there is a move that will capture 6. So, this particular position of international drafts where the double circles are kings, this move is actually forced. This is the move by black that captures the largest number of white pieces. And therefore black must make this move. In actual drafts tournaments, if your opponent notices that you have made a move that you could have made a better move that captures more pieces, they will wave the judge over, point out the move that you didn't make, and you lose. Or, depending on the tournament, they say, no, back up and do the other move. You made an illegal move. Maybe if they're nice, they'll say back up and do the right thing. But actually, no, it's just against the rules. It's just not a legal move to take less than the maximum number of pieces. And so, in this case, it really looks like black is about to win. Now notice, black can't capture any more because there are 2 white pieces in a row. You have to only jump over 1 white piece when you make a capture. If there had been a gap between those 2 and some space beyond it, then he could have jumped over and won. And then after black makes that move, white is forced to win. So from this position over on the left, black must move in a way that will lose them the game. So this is a winning position for white. And the last subtlety, which only matters because there are flying kings, is captures come off at the end. Right. So when you're actually playing this game, what happens is black will go hop, 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 and then all those white pieces will come off. You cannot jump over the same piece more than once. Once you've captured a piece, it's dead. You can't capture it again. It sits there being an obstacle until your move is over. With these 3 rules in place, playing the game legally is NP hard. Not winning, playing the game legally, following the rules of international drafts is NP hard. And there's a reduction which is mostly due to Bob Hearn, who was a PhD student at MIT at the time, that there's a reduction from the directed Hamiltonian Cycle problem, which we know is NP hard because 3-sat is NP hard, which we know is NP hard because circuit-sat is NP hard, which we know is NP hard because Cook and Levin are Spartan. And the basic outline is I take my graph and I produce a layout of checkers that looks vaguely like this, where I have a little rabbit-shaped gadget for every vertex. These are connected, in this case, a directed graph by edges which leave either, they leave from the left ear and they go into the right ear, and they have this 45-degree square thing. So in order to make this work, I have to describe what happens inside each of these rabbits, what happens to make the checkers turn here, and what happens when things overlap. And so there are some details in the notes, but what you end up with is, here is a position in international drafts generalized to an arbitrary size board, which is constructed from a graph where if the graph has a Hamiltonian cycle, then white can capture every one of the black pieces inside these little rooms. Those white circles, by the way, are pieces that are frozen that can't move. Right? They're black pieces you can't jump over. They're white pieces you can't jump over. So if you can capture all of the pieces in these rooms, the only way to have done that is to follow a Hamiltonian path through the original graph. Right? So the original graph has a Hamiltonian path if and only if you can capture all these pieces. But if you can't capture all these pieces, then in particular there's some room that you can't capture. So there's actually a big gap in the number of in the values that you can, the number of pieces that you can capture. It's a lot if the graph is Hamiltonian, and it's not a lot if it isn't. And so it's NP hard to decide that. Details are in the notes. I'm happy to take questions, but y'all can leave.